and we'll go from current slide, if I can get that to do its thing, and we're starting on the general power rule for integration, so this is not the right slide. I should have checked that first. We've already done example 4. Whoa, but not 7. There we go. There's the slide we start on. All right, now any questions at all? Calculus, any other kind of questions at all? If any of you have submitted any work over the weekend, and this room is getting a little stuffy, hang on just a second. The morning is warming up outside, and I have to close the door because my wife's working at home today, so I have to have the door closed, and it gets a little stuffy, so I turned on the ceiling fan. All right. Where was I? What was I going to? Oh, if any of you did turn in any work, this is why I was trying to clear emails today, because I had almost no opportunity to over the weekend. Every spare moment I had this weekend, I had to be working on spring schedule. They sent it out Friday, and we had to have it in, and so it was a mess. It was really completely screwed up, so I had to do an entire schedule, and it was pretty bad. But I think I got it all done, and sometime late yesterday, so I started trying to print things and getting things from students. So I'm just barely got started on that. So if you did submit something and you haven't heard back from me, that's probably why. All right, any questions? All right, we're starting today on page, it's chapter 5, integration, 5.5, integration by substitution, and my for some reason my microphone and headset attachment is just getting all tangled up. Okay. Okay, starting on chapter 5, integration, 5.5, section 5.5, integration by substitution. We're on page 337, and this begins the general power rule for integration, which is where this slide picks up. Okay, so with that in mind, here's what it says, and I know you can read it, but one of the most common used substitutions involves quantities in the integrand that are raised to a power. We've seen several of those already. Because of the importance of this type of substitution, it's given a special name, the general power rule for integration. And here's the theorem 5.14, which gives that. If g is a differentiable function of x, and you have the integral of g of x raised to the nth power, followed by the derivative of g of x, then your u substitution, let u be the g of x, and then the du will be g prime of x dx. So there's your u prime, or du, and this is the u to the nth power. So what you do is the function g to the x raised to the n plus 1 power over n plus 1, just like we've always done, plus c. Now this only works when n is not equal to 1. For any other value n, now time out for a moment here. A lot of times in math and in computer science, they will use n to represent an integer. Notice here, you do not need n to be an integer. Any real number. Now most of the time we don't do irrationals this way, so don't sweat irrationals yet, but certainly any rational number, n, it'll work, except n equal minus 1, because if n was equal to minus 1, you would wind up with a 0 in the denominator. We can't have that. Okay, and of course you know what it would be if this was g of x to the minus 1 times g prime of x dx. Someone tell me, please, what would that one integrate to be? 1 over x dx? What's the integral of that? Natural log of x. So if n is equal to -1, that would then be natural log of g. Okay, that's it, plus c. Okay, so that's how it works. Let's see some examples. And any question on it before we go? It's what we've already been doing. They just want to give it a special name, it seems like. Okay, so here we have it. And I don't care about this stuff here. Let's just pretend that we are solving this problem without their anecdotal help here. Okay, right here. Here we see a u raised to the 4th power, and then we want, so let the innermost part of the most complicated part of the integrand, that would be this right here, let that be our u. Let u equal 3x minus 1. That's it. Always follow the let with a then. Du is equal to, and what is the derivative of 3x minus 1? Anybody? Anybody? 3 dx. Always follow a d with a d, okay? And here's your du right there, and here's your u to the 4th here. So that's where they get this. This is then equal to the integral of u to the 4th du. And we could do that, right? What would that be? Integral of u to the 4th du, u to the 5th over 5 plus c, of course. But let's go back and plug in what u is. That's, I like to put the 1/5 in front, so I'm going to do that. The book may not do it this way. 3x minus 1 to the 5th plus c. That's it. Done. Okay? And that's what they're doing too. Let's see how they do it. That would be, they did it this way. Whoops, sorry. 3x minus 1 to the 5th over 5 plus c. Done. That's it. Pretty simple. Okay? Let's see if we can do the B one here. I know this has gotten kind of messy. I wish there was some way to erase this. I haven't figured out how. Let's see. That doesn't do anything. Okay, I thought maybe it would. Okay. Here, what do we have? Whoa. We have a product here. You know what I would think? Well, okay. They sort of give it away here. The most complicated, the more complicated of these two would be this one. Let's try that to be our u. Let u equal e to the x plus x. Follow that by then. Du is equal to what? Derivative of e to the x is e to the x. Derivative of x is 1 dx. Always have a d with a d. Okay? Well, here's the du right here. Here's the u right there. So this is pretty simple. Just the integral of u du. And believe it or not, that is a power rule. N is not minus 1, it's 1. So this would be u squared over 2 plus c, which for our case would be e to the x plus x. Now the way they wrote it last time was over 2, which is fine, plus c. So that should be the answer they get. Let's see what they get. Any questions on this? I wish y'all were answering more so I wouldn't have to be doing all the talking, but I know y'all are shy, so speak on up. Okay, that's, well, I left off the 2, didn't I? Okay, there it is. e to the x plus x squared over 2, and that's exactly what they got, plus c. There's their answer. It's pretty straightforward. Any questions on that? Now, I will admit what my first tendency was. Well, let's just multiply these together, FOIL them, until I noticed, wait a minute, this is a derivative of that one. Most of the time when you have two binomials multiplied together, one won't be the derivative of the other one. This one was a bit bizarre that it was. So you could have multiplied them together, come out with the same answer. It probably would have been in a different form, but would have been perfectly correct. Any questions? Let's do the C one. All right. Now, yes.
How did you get the on B? How did they get the 2 in the denominator? Is that the answer?
No, okay, from here. Right. Okay. Where is it? Right down here. I know it's hidden. The integral of u du is u squared over 2. And that's where the 2 in the denominator, that's where the square came from. So this, yeah, well, that's the, going back here. Okay. Anytime you have u to the n, we had u to the 1 du, that'd be u to the n plus 1. 1 plus 1 is 2 over 2 plus c. Got it? Make sense? Good. Good question. Please ask. Please ask. All right. All right. Now we're doing this one. Okay. I know it's messy because of the writing in there. But what is the yuck? What is the innermost? What's the most complicated part here? Obviously the square root. What's the innermost part of that? The 3 or x cubed minus 2. So let that be our u. Let u equal x cubed minus 2. Then, always follow the let by then. Du is equal to what? Derivative of 3x squared dx. Perfect. And there it is. 3x squared dx. There's your du. This is u to the what power? Square root is 1/2 power. So this becomes the integral of u to the 1/2, that's the square root of u, du. Integrate that, and what does that become? Add 1 to this, n plus 1. Remember I said n doesn't have to be an integer, it could be a rational number. 1/2 plus 2/2 is 3/2 over 3/2. Well, I like to write that as 2/3. Okay? And then plus c. So that would be, I like to write it this way. The book probably won't, but I'll do it this way. 2/3 of x cubed minus 2 to the 3/2 power plus c. Now, you could have written that as the square root of x cubed minus 2 cubed under the square root, or the square root of x cubed minus 2 with the cube outside the square root. It doesn't matter which. Let's see how the book wrote it. Okay, they wrote it this way. They wrote it over 3/2, which is sort of awkward, but it's okay. Let's see if they took it one more step. Yes, they did. Then they wrote 2/3. Look at that. They wrote just like I did. X to the 3/2 minus 2 raised to the 2/3 x cubed minus 2 raised to the 3/2 power plus c. Exactly like we did. Now, remember, if you wanted to get it back in square root form, you could have put this x cubed minus 2, the square root of that, and then either cube what's inside the square root or cube it outside the square root. It doesn't matter. But why go to that? It's so much easier to work with in exponential notation. than in radical notation. So I wouldn't go back. The book didn't here. Sometimes they will. That's what makes it hard. You don't know which way they're going to do it. All right, any questions on those three? That's example 7. There are 2 more coming. So let's go, unless there's any question on these 3. All right, let's go to D. All right. Now I'll try to write above on this one so I won't be messing up as much below. What is the most complicated part of this problem? Obviously the denominator. And the denominator is raised to a power. Okay? So just let the innermost part of that complicated part be your u. So that's going to be let u equal to that innermost part, 1 minus 2x squared. Follow that by the then, can't spell it, but got it, du, and the pen is doing weird things, is what? If this is u, what's du? Anybody? Negative 4x dx. Always have a d with a d, right? And that's exactly what we've got here, negative 4x dx. There you have the du over u squared, which would be u to the minus 2. That's how I would express it, so I'm going to write it that way. The integral of u to the minus 2, that's the u, 1 over u squared is u to the minus 2 du, because this is the du part right here. Okay? And what would that integrate to be? I'll give you a hint. U, increase the exponent by 1, minus 2 plus 1 is minus 1, over minus 1, which I'm just going to put a minus in front, plus c. Now, you remember, this can be a minus 1, this in here. If this is a minus 1 in here, the answer is not a power rule, it's the log rule. Okay? But this was not a minus 1 in here, it's a minus 2, so you can still do the power rule. And this translates to be the u, exactly. Negative 1 over u, but u is that, so it'd be negative 1 over 1 minus 2x squared plus c. So that's what we get as the answer. Let's see how the book does. Well, they wrote over me anyway, didn't they? Got the same thing. They put the minus 1 in the denominator. I put it in the numerator. It doesn't really matter. And that became minus 1 over 1 minus 2x squared plus c. Perfect. Good for them. Any questions? Does that make sense? All right, let's move to E. I think that's the last one. Oh, we jumped to a trig function. Okay, what's the most complicated thing in your integral? You tell me. The squaring of the cosine. So take the innermost part of that, which would be just the cosine, and let that be the u. So let u equal cosine x. Very good. Follow the let with a then. This has a little bit of a problem with it. Du is equal to, what's your, you're right, negative sine x. One more thing. Dx, perfect. Well, here we have a positive sine x. So what we're going to do is multiply both of these by minus 1. So a minus du is going to be sine x. So here's your minus du, and here's u squared, right? So this becomes, since this is the last problem, well, I'll do it up here. Minus, I'm going to pull the minus on the outside, the integral of u squared, that's the cosine x squared, du. It was a minus du, but I put the minus out here and here. Well, we know what that is, right? minus antiderivative of u squared. No, add 1, yeah, u cubed over 3, you're taking a derivative, okay, and then plus c, and then plugging back in whatever is a minus cosine cubed x over 3 plus c. Okay, they may have written it minus 1/3 cosine cubed x. Let's see how they wrote it. That's exactly how they wrote it. Minus cosine, well, they wrote cosine x in parentheses cubed. This means the same thing. I'm lazy. I didn't want to write 2 parentheses and put the 3 on the outside. I wrote it that way. Means the same thing. Let's see if, they didn't do that. All right, any questions on example 7? How to use the general power rule for integration. Nothing new here. We've been doing it all along, okay? They just call it something special. And it is. It's something that's used a lot. Excuse me, just a minute. My head is closing up on me. Let me get a little, sorry. Carbonation, see if that will maybe loosen it up some. I don't know. Tastes good anyway. All right, any questions on example 7? Please ask. Any questions? All right. Then we move to, let me see if we move to, there actually was the bottom of the page there that probably is worth a little bit of statement. The slide, the PowerPoint skipped it, but I think maybe it's worth saying something about. And here's what, so let's go back a slide and go to the whiteboard. Okay, now I'm going to have to do my maneuvering. Get my taskbar here, up and over. Okay, and I've already got that stuff moved, so let's move this to the left and up as far as we can. Whoops, that's as far as I can go left, and here's as far as I can up. Now you probably just saw white and says, what is he talking about? But I have a limited space here. Some integrals whose integrands involve quantities raised to powers cannot be found by the general power rule. It says here's 2 examples. Here's the first one. The integral of x times x squared plus 1 squared dx. Now, I really don't see what their problem is, except one minor detail we've already dealt with. What would you assume the u would be here?
X squared plus 1.
Exactly, x squared plus 1. Everything's looking okay, I think. Then what?
Du equals x dx.
2x dx.
Oh, 2x dx.
All right. You were trying to make it too easy, weren't you? Well, we don't have a 2x dx. We have an x dx, so let's divide this side by 2. We've done this already, okay? Divide by 2. And that way we do have an x dx, and this will just be du over 2. So what do we have now? We have a 1 over 2. I'm going to pull that 1/2 on the outside, this one. And then what we have inside the integral is u squared, that's your x squared plus 1 squared du. It's a du over 2, but I'll put the out here. And this is just the general power rule. 1/2 of what? It's antiderivative. U cubed over 3 plus c. And that would be 1/6 x squared plus 1 cubed plus c. Now, I don't see what the big deal was. That one it worked fine. Sorry. Okay. That one it worked fine. The second one of these was this one. And I see what their problem is now. Okay, I said, what's the big deal of doing the 1/2? That was the only thing we did differently. Okay, here's the second one. This is the one you have problems. X squared plus 1 squared dx. There is no u substitution here. But it's still not a bad integral, because all you have to do, if I could get my pen to show up, there it is square the binomial. Remember how to square a binomial? Square the first term. Goodness, the pen is all over the place. X to the 4th plus twice the product of the 2, so that's going to be plus 2x squared plus the square of the last, plus 1. And we can just use our regular old rule here. What would this be? Antiderivative of x to the 4th would be don't tell me you've forgotten this one already. X to the 5th over 5, that's just a power rule, plus, and this would be a 2x cubed over 3 plus x plus c. So don't force a u substitution when it won't work. Try something else, like multiplying them together. That might do. Now, if that was a square root, you're in big trouble. Okay, we'll get to how to do that later. Okay. So, any questions on that? All right. So, they didn't even carry them out all the way, but they did. Oh, goodness, this is such a big, heavy book. Okay. So, any questions on this before I close the, whatever this is called, the whiteboard? Go back to the slide set if I can get my pen to show up. Any questions? All right, back to 5.5. Back to current slide. And that's where we left off with that. Now we're doing something different. Okay, two things different here. Number one, our u substitutions so far have been dealing with indefinite integrals. Now, you could, when you got to definite integrals, just do the definite integrals the same way you did the indefinite integrals, but then at the very end, go back and put the values in. That's okay. It's doable. It is something you tend to forget and screw up on. So if there's any way you can keep from doing that, do it. And here's what their suggestion is, and it's a great one. Use a change of variables if it makes it easier for you. And most of the time it will. So this is going to be something new here. Number one, definite integrals, and then how to do change of variables. Because why? Definite integrals never have a plus c. So we need to have something to actually evaluate them, not just having a plus c. So let's see what we have. When using u substitution with a definite integral, it is often convenient to determine the limits of integration for the variable u rather than converting back to antiderivative back to the variable x like we were doing for indefinite integrals. and then evaluate using this, and then later evaluate using the original limits. It just saves you several steps, and I'm lazy enough to do it. This change of variables is stated explicitly in this next theorem, theorem 5.15, and that is if a function u is equal to g of x has a continuous derivative on the closed interval a to b, those are the limits here, and f is continuous on the range of g. Now the f is the outermost function. It's evaluated at the values of g, which would be the range of g. So f has to be continuous on g, and u equal g of x has a continuous derivative on the closed interval a to b. So they really make this difficult seeming, but here's what you do. You do the integral from a to b of f of g of x times g prime of x. That's your simple kind of anti-chain rule, you might say. If you were taking the derivative of f of g of x, you would have f prime of g of x plus times g of x, g prime of x. Well, now you're doing the antiderivative of it, and you get f of u, let g of x be u, g prime, let u equal g of x, du would be g prime of x dx, and this would just be f of u du. Take the antiderivative of this, but notice what they did here. Since they had the a and b here, and you did the substitution, let u equal g of x, evaluate g at a, that's going to give you a number. Evaluate g of b, that gives you a number. That's going to be your new limits for this one, because these are the limits for u, because u is g of x, and then do the integration. It saves you a step. This probably is a little confusing looking because it's a lot of blah, blah, blah. Let's actually do one. Here it is. Okay? Now, we're going to start it very similar to what we did before. What is the most complicated part of this problem? Yeah, well, that's the innermost part. The most complicated part is the cubing, so let's take the innermost part. So let that be our u. Let u equal x squared plus 1. Very good. Perfect. Okay. What do we always follow the let with? And du is equal to what? 2x dx. Perfect. Okay. Now we don't have a 2x dx. We have an x dx. So let's divide this by 2 and divide that by 2. That'll wipe out the 2's here. Now we have, this is du over 2 here, and this is u to the third. But before we write down the integral, what we're going to do is go back to this thing here. When x is equal to 0, that's what this is meaning, x equals 0, what is u equal to? 0 squared plus 1. And when x is equal to 1, that's what this is saying here, u is equal to 1 squared plus 1, 2. High level math today. 1 plus 1 is 2. Okay, good deal. Okay, now you do your integral in u, and that would be the 1/2 that we had here. Didn't leave enough room for it, but that's the 1/2. And then what we have here is u cubed du. U cubed du. Okay? Now, what would that be? 1/2 of antiderivative of u cubed over 4. Okay? And evaluate that from 1 to 3, 1 to 2. Don't put your plus c. You don't need a plus c in definite integrals. Okay? And here, what I'm going to do here is bring the fractions out. That would be 1/8, and that would be 2 to the 4th power. Anyone know what that is? Two times 2 is 4, times 2 is 8, times 2 is 16. 16 minus, see I pulled the 4 on the outside with the 8, with the 2, so it's outside. So all I'm evaluating is u to the 4th minus 1. 1 to the 4th power is 1. 1 times 1 is 1 times 1 is 1 times 1 is 1. Okay, so this would be 15/8. When you have a definite integral, you generally have a numerical answer. You won't have x's or u's in your answers. So that's why we went on and did the substitution. All right, that's what our answer is. Let's see what they get. To evaluate this integral, sure enough, they chose the same u that you did, u equal x squared plus 1. That then gives you a du of 2x dx, which is exactly what we did. Before substituting, determine the new upper and lower limits of the integration, and you just let, in this expression here, let x equal 0 here, plug it in here, and you get u equal 1. That's going to be the lower limit. And when you plug in the upper limit here, that'd be 1 plus 1 is 2, so that gives you the upper limit. So the lower limit when x equals 0, you get 1. Upper limit when x equals 1, you get 2. So put those in your integral, and you have, this was the original. Now it becomes a 1/2 because when we did the, they didn't show it. But here, when you divide both sides by 2, let me do it. Okay, the x dx here, I can't draw well. X dx here becomes du over 2. So pull the 1/2 on the outside. That's where that came from. And then you have, now why they kept this, oh, okay, I see what they did. They said this is this times 2x dx. They brought the x over here and did your 2x here, but because you multiplied by 2, you divided by 2 out here. Same thing we do, except they took more steps doing it. Sorry about that. I don't find that's any clearer. If you do, do it that way. Please, it's correct. Okay? Now, what we're going to change that to is 1/2 on the outside times u cubed du. That's exactly what we got. The 1/2 came from 1/2 du, and evaluate that. That's going to be 1/2 of u to the 4th over 4 evaluated between those two. Now what they do, which is fine, they evaluate it in here. I took the 4th outside because it just made it easier. I didn't have to divide twice. But what they did was this way, and it works too. This was again was 16/4, which is 4, minus 1/4, which is 1/4. And now you have to do least common denominators and do it all over again, and that gives you 15/8. They just skip a lot of steps and show, oh, that's the answer. And that's exactly what we got. 15/8. Okay? Right. Where is my pen? I can't find it. Oh, there it is. Okay. 15/8 right here. And that's what they got here. 15/8 here. All right. Same answer. Any questions on that? New little twist, but just like I think definite integrals are usually easier than indefinite integrals, because you have to carry around all the variables and put a plus c and not forget to do that, whereas definite integrals evaluate and get a number. Okay? Any questions? Excuse me just a minute. My head's still clogging up. I don't usually drink in class, but this is not my bedroom, but a bedroom in our house, so I'll drink in here. All right. That was example 8. Notice that when you obtain the same result when you rewrite the antiderivative 1/2 u to the 4th over 4 in terms of the variable x. That would be 1/2 of x plus 1 to the fourth power. This is like we would do it if we were doing indefinite integrals over 4. Evaluate that from 0 to 1. Well, what do you get? You get 1 to the fourth. I'm sorry. The upper limit is 1 plus 1. So it's 2 to the fourth. You get the same answer there, minus 1 to the fourth. You get the very same answer. It's just you have to convert this, the u, back to the x, and then the x from here. Why not just do it at once? And you get the same answer, 15/8. Good deal. So if you prefer it that way, do it that way. Perfectly fine. You get the same answer. Just, to me, a lot more opportunity to make an error here. All right, before we get to even and odd functions, they have example 5, which is not given on the slide set. So let's if I get on the right pad here, let's go back to our whiteboard. Any questions before we leave that one? Okay, can I erase this scratch? All right, so let me get this big old heavy book back down here in front of me so I can read it. It's just that I get a glare and it's a pain in the neck to read from over there. So here it is here. Here's example 9, top of page 339. Here's the integral. The integral from 1 to 5 of x over the square root of 2x minus 1 dx. Now, wouldn't you figure it that the one they do is really straightforward on the slide set, very straightforward, and then the one they don't do, they skip over, it has a lot of nuance in it. This has nuance. What would you choose as your u substitution? Yuck! That was totally uncalled for. Okay. Now, what would be your u substitution here? Any guesses?
2x minus 1.
That's it. 2x minus 1. There's your u substitution, because it's the innermost part of the most complicated part of that integram. Obviously, the most complicated part is that radical in the denominator, and the innermost part of that is 2x minus 1. What's then your next step? Then du is equal to 2 dx. You're right, and I'm a little surprised too, because that's not what we have up here, is it? We don't have an x dx. They want a 2 dx. Well, there's no x, but there's no 2, so let's get rid of the 2 down here, divide both sides by 2, and we'll just use a dx. Okay. But we've also got some manipulation. We've got to do something with this x. But here's what we can do with that. Let's solve this equation for x. So what would be your first step? Add 1 to both sides. I told you this is quite a more complicated problem. This gives us u plus 1 is equal to 2x, because these ones add to 0, right? Well, we still got to divide by 2, because we don't have a 2x here, we have an x, so make this a 2 here and a 2 there. Okay, now we've got what x is, so let's rewrite this integral to be the integral. I'm going to leave off the units for now. Now what do we have? We have 1/2 out front from here and another 1/2 out front from there, so that's going to be a 1/4. Okay, and then our x is, I already took care of the 2 out front, u plus 1 Okay, 1/2 of u plus 1, but that first 1/2 is out there, times, this would be u to the minus 1/2, right? U to the minus 1/2. Square root of u. That's what this was. That was our original substitution. Agreed? And then we have our du. The du over 2, but that's the other 2 that's out here. Now, what we haven't done is figure out what our limits are. So let's go back and do our limits. When x is equal, where are you? There you are. When x is equal to 1, u would be 2 times 1 is 2 minus 1. U is equal to 1. That's not bad. When x is equal to 5, though, this would be 2 times 5 is 10, minus 1 is 9. So here are the new limits. If this stinking thing would draw, that is a 9 up there. Okay. So what do we have? Don't forget the 1/4. That incorporates this 2 and that 2. Okay. Now, I think I'll write my integral sign again from 1 to 9, because what I'm going to do is distribute this across here. So u to the 2/2, that's what this is, u to the first, so u to the 2/2, times u to the minus 1/2. You keep the base, u, add the exponents, 2/2 minus 1/2 would be 1/2, right? 1 times this would just be plus u to the minus 1/2 du. That was just, distributive property, and you're dealing with the rules of exponents. Okay, so now we're ready to do the integration. Okay, what's the antiderivative of u to the 1/2? Times 2 over 3. Excellent. Plus, that will disappear in a minute. Well, what's the antiderivative of u to the minus 1/2? Well, it would be over 1/2, which would be a 2 here. Okay, you got it. And that's evaluated from 1 to 9. Now, before I start doing my evaluation, though, I'm going to look at this and say, wait a minute, I've got a 2 here and a 2 there. So I'm going to divide out a 2 from these 2 and here. That gives you a 1/2. So now we're down to 1/2. I think I'll leave the 3 in there for now. All right, now we do our evaluation here. Since it's to the 2/3 power, 3/2 power, I like to do the square root first and then cube that. So when u is equal to 9, the square root of 9 is 3. 3 cubed is 27, and 27 divided by 3 is 9. Okay, we're right back to 9. Okay, plus, and the square root of 9 is 3. Minus, now we're doing everything in here. Don't worry with the 1/2 yet. The square root of 9 is 3. 3 cubed is, square root of 1. We're doing the lower one now. Square root of 1 is 1. 1 cubed is 1. And that divided by 3 would be 1/3. And then you have a minus here, the square root of 1, which is 1. Okay. Now the rest is just math. Unfortunately, it's math with fractions, so let's do it. That would be 1/2 of, well, 9 minus 1 is 8 plus 3 is 11. Minus 1/3, that would be 10 2/3. Now I'm doing it as mixed numbers. Let's rewrite that as 1/2 of 3 times 10 is 32 thirds. Is that right? I'm surprised at that. And 2 will go in the 32 is 16. So I get 16 thirds. Now I may have made a dumb mistake here, but let's check and see. How did the book? Oh my goodness, look at that. They got 16 thirds as well. So that's how we do it. So this, not exactly as straightforward as the previous one was. Number one, your U substitution here is a correct U substitution, exactly right, but you don't get your du to be anything like this. So to get this x out of here, you have to take your U substitution, rearrange it to find out what x is, and xu plus 1 over 2. Your dx was du over 2, so you have 2 over 2's here, so that's going to be a 1 over 4. And your numerator here is going to be u plus 1. Your denominator was u to the minus 1/2, the square root of u, which is u to the minus 1/2. Well, u to the 1/2 in the denominator is u to the minus 1/2 in the numerator. Always get it up in the numerator if you can. And once you do, now you can distribute this. And when you do, that gives you u to the 1/2 plus u to the minus 1/2. When you take the antiderivative of that, that becomes 3/2 times 2/3, and this becomes 1/2 times a 2. And I got rid of one of the 2's here, kept this 1/2 out here. Then do your evaluation. The square root of 9 is 3. 3 cubed is 27, divided by 3 is 9, plus the square root of 9 is 3, minus the square root of 1 is 1, 1 cubed is 1, 1/3, minus the square root of 1 is 1. Okay, so these two minuses come from being the lower limit. And then the rest of it is just fractions, is all it is. 12 minus 1 is 11, minus 1/3 is 10 2/3. That's 32 thirds. 2 will go into 32 16 thirds. That's our answer. Any questions on that? Okay. Now, let me go back to the slide set, I think, just to see where they pick up and go. 5.5. Okay, we did that one. Okay. Now, let's go back to our whiteboard. The bottom of this page here is saying geometrically, I'm going to set this aside for now. Goodness gracious, this thing's heavy. Geometrically, you can interpret the equation, this equation right here, this one right here, this equation. It's not really well, it kind of is. They give it yet another meaning here. Okay. They're taking our result here. Now, I don't know what they're doing. It's a real big stretch of what they're doing there. And I'm not even sure why they're doing it. It seems like they're just muddying the waters terribly. Goodness gracious. Bottom half of page 339, I see absolutely no reason to go through that agony to get something, because it doesn't look like anything close to the right answer. So I have no reason, I can't quite figure out why they're doing what they're doing, and it certainly makes nothing any easier to do. Oh, I see. Okay. Going back up here, oh, I see exactly what they're doing. They did a different U substitution from the one we did. And this is a way to do the problem. I was going to say, where did they come up with this? Their U substitution was this: let U equal to the square root of 2x minus 1. Now, I would never recommend doing that. I'd say the innermost part of the most complicated part. Ours worked pretty easily. If you go through what they do, it works well, it comes out exactly the same answer. It has to. But what you have to do, yuck, I would never have chosen this. This is the same as 2x minus 1 to the 1/2 power, and then your du is equal to 1/2 2x minus 1 to the minus 1/2 power dx, okay, and that is the same as 1/2 u dx. Now, I don't know. No, I'm sorry. They did something else first. Here's what they did first. Let me erase that. This is just, I never would have done it this way. It's legal. Now I can't get it to erase. And I don't know why it won't erase now. But it won't. I cannot get this thing to erase. So I'm going to have to just go through it. They don't quite do this. And I'm not sure it's worth taking your time to do it. What they do at this point is say u squared is equal to 2x minus 1, and then they solve that for x, and that gives us exactly what we had before, I think. Well, close to it anyway. So x is equal to u squared plus 1 over 2. Yeah. And then they proceed from there, and they do come up with the same answer. Okay? You do your dx from there and move. So that's just another way to do the problem. But then they take that, their way of doing it, and talk about do a geometric interpretation of it. And it's just so much harder to do. I mean, forget it. Okay, no wonder the slideshow did away with it. Okay, sorry about that. I'm sorry I even brought it up. I thought they were showing a different type of problem. They weren't. They were just screwing around with that one. Okay, so let's go back to our PowerPoint. Okay. Well, wait. Go from current slide. Okay. Integration, and this is the top of page 340. Integration of even and odd functions. Okay. It's a handy little shortcut when you can recognize it. Even with the change of variables, believe it or not, integration can be difficult. Occasionally, however, you can simplify the evaluation of a definite integral over an interval that is symmetric about the y-axis or about the origin by recognizing the integrand to be either an even function or an odd function. Now, if you remember back in pre-calculus algebra, they usually talked about even and odd functions, but then what they sort of neglected to tell you that most functions are neither even nor odd. Now, when you get over into the trig functions, they're almost always even or odd. So that's nice about trig functions. But most functions in general, excluding the trig functions, are not even or odd. Some are, and when they are, take advantage of it. Okay? Now, here is what an even function looks like. Whatever is happening on one side of the y-axis, the same thing's happening on the other side. So if you're doing the integral from negative a to a, guess what? It's just exactly twice the integral from 0 to a. That's what their point is. That's so easy to do this way, twice this integral of this function from 0 to a, rather than having to go from minus a to a. Because usually substituting in a 0 and a definite integral is so much easier than substituting a negative a. That minus sign is just there to trip you up and make you make mistakes. So please, if you can avoid that, do it. Now, if it's an odd function, whatever's going on this side, the opposite's going on this side. Okay? So therefore, if you're integrating from a symmetric interval, minus a to a, this is going to be a positive area that's going to be exactly the same size of a negative area, and they're going to add to 0. These will be twice what 0 to a is. This will add to be 0. Okay? That's what the point is on integrating even and odd functions. Okay. So here's the theorem that backs up what we just said. Let f be integrable on some closed interval minus a to a. Notice that's an symmetric interval. It goes minus a on one side, plus a on the other side, exactly the same distance on both sides. If that f happens to be an even function, not a neither, not odd, but even, exactly even, then just immediately change that to be twice the integral of that same function, f of x, from 0 to a, because that's what it's going to be. Because it's symmetric about the y-axis, so just double what you get from 0 to a. This is generally the antiderivative is exactly the same. It's easier to evaluate it from 0 to a than from minus a to a. Believe me, that minus sign will cause you headaches, problems. You'll trip you up every chance it can. Just double from 0 to a. But if it's an odd function and you're doing that, don't even mess with it. That's going to be 0. You know it will because it's odd. Whatever is happening on the left is the opposite of whatever is happening on the right. You're going the same distance to the left, same distance to the right. It's going to add to 0 every time. All right, so here we have one. Evaluate this definite integral. Oh boy. How would you approach this problem? Rather strange little problem, isn't it? Okay. Now, on the one hand, I would be tempted to factor out a sine x cosine x, and that leaves you a sine squared x plus 1. That doesn't really help you. Okay? So I think the other thing to do was just go for it. Just make this two integrals. Okay? Make this from minus pi halves to pi halves. Notice it is a symmetric interval, and this will then have a dx here. Okay, do two of these. Okay, now here I would do a u substitution. What would you choose? Anybody? Anyone? Earth to class, come in, please.
Sine creates
Yeah. Well, yeah, okay, you've already done the integral. Okay, let's just use sine x. The innermost part, the most complicated part of that problem. The most complicated part is the cubing function. The innermost part is sine x. Then, du is equal to u is sine x, du is cosine x dx, right? Pretty ugly x there. And that's exactly what we've got here. So this becomes the integral from minus pi halves to pi halves of u cubed du, right? This part is your du, this part is u cubed. Agreed? Plus, let's do the same thing here. It really doesn't matter which you choose. I think I'll let the same one. This will then be same thing. This will be your du. That would be your u. This is the integral from minus pi halves to pi halves of u du. Now, what do you notice about this function? Rather strange word, isn't it? Another way we could call it would be, it's kind of odd. It is odd. Integral of a symmetric interval of an odd function, 0. This one, also odd. Exponent is 1. That would be plus 0 equals 0. That's all, folks. Now, if either one of those turned out being even, then we would have doubled the integral from 0 to pi halves. But both of these turned out odd. Okay? And sure enough, that's what they got. Let f of x equal that. Oh, man. This is not how I would do it, but it is absolutely true. Then plug in and see what f of minus x is. Well, that would be sine cubed of minus x. Well, sine of negative x would be minus sine of x, because sine is an odd function. Cosine of negative x is cosine x, so that's an even function. So you have an odd times an even, that gives you odd. And then you have an odd times an even, that gives you odd. But carrying it out the way they're doing it, that would be minus sine cubed x times cosine x, minus sine x times cosine x. And again, I think, why in the world do it this way? That's minus f of x. That's what they were trying to do. This is exactly opposite of what your first thing is. So that is an odd function, and then once you see it's an odd function, you know the integral of a symmetric interval of an odd function is 0. My goodness, it was so much easier to do than a u substitution, but this works just as well. In my mind it was. Maybe you think this is easier. And if you did draw the graph of that here, surprisingly, it comes out looking like that. Not quite like a sum function, but close to it. And the same area is over here that you have up here, so therefore they add to 0. All right. Any questions on that? All right. However, because one lies below the x, that's one's above, the integration produces a cancellation effect, giving you 0. That's the last of section 5.5. Homework exercises here. And by the way, the concept check at the top of the page, 341, not a bad idea to think through that. I would say a very good idea. Okay? But then homework exercises here, either 5 or 7. They're both at Calc Chat. 5's at Calc View. Any of the odds 9 through 27. they're all at CalcChat. 15's at CalcView. 29 or 31, they're both at CalcChat. 29's at CalcView. 33 is at CalcChat, or should be anyway. We didn't do one like that in class, but that's a relatively simple process to go through. You have to have a computer to help you do it, but they've done that for you, and then you go from there. Then do any of the odds 35 to 55. They're all at CalcChat. 41's at CalcView. Any of the odds 57 to 63, they're all at CalcChat. 59's at CalcView. 65 to 71, they're all at CalcChat. 65's at CalcView. 73 through 83, they're all at CalcChat. 77's at CalcView. 85 or 87, they're both at CalcChat. 85's at CalcView. Either 89 or 91, they're both at CalcChat. Now they suggest here you might need a graphing calculator or a graphing utility. I think you can probably do these on your own, but if they do give you problems, then use one if you got it, otherwise skip them. Then either 93 or 95, they're both at CalcChat. 93's at CalcView. And then 97 and or 99. You can explore doing 101 if you'd like. They should all be at CalcChat. You can do either, I'd say any of the odds 103 through, goodness gracious, 109. They should all be at CalcChat. This goes on and on and on, doesn't it? 111 should be at CalcChat. It introduces probability here, which certainly is a fine thing to look at. 111 deals with that probability, so you can look at that one as well. Any of the odds 113 to 117, they're all at CalcChat. And then either 119 or 121, they should both be at CalcChat. Okay. Any questions on 5.5? Okay, how are we doing on time? Let's take a look and see. Oh, we got not quite 30 minutes, but we got sometime 20 minutes, 21 minutes. Okay, that's time to close out this one. And I know we lost our sharing, but let's go to 5.6. And here, my taskbar moved right up in my way again, so let me scoot it out of my way. I know it doesn't bother you, but it blocks what I can see. And we'll go from current slide. Goodness, I got so much drainage this morning, I really don't know why. It says screen sharing is stopped, but y'all can see that, can't you? Can you see 5.6 indeterminate forms of L'Hopital's rule?
Yes, sir.
Yeah, okay, good deal. Okay, so this is 5.6, indeterminate forms and L'Hopital's rule. This is a pretty interesting story here. Well, I can't get it to advance until I click on the slide, and then it'll advance. Our objectives here: recognize limits. Hey, we seem to have stopped doing integration, certainly substitution. Now we're looking at limits again. Okay? Recognize limits that produce indeterminate forms, and then maybe apply L'Hopital's rule to evaluate a limit. Well, the question may come to mind, who in the world is L'Hopital, and what is his rule? And if you do choose to write on that, you're going to discover a pretty interesting little phase of calculus history. L'Hopital, he was a French, may have even been a nobleman. I don't know, I can't remember now if he was or not, but he obviously had money, but he was quite a good mathematician. He studied under some real giants, one of those being, I believe it was Johann Bernoulli. There was a whole family of Bernoullis. They were brilliant mathematicians. pains in the neck as people, I gather. Don't think they had particularly easygoing personalities at all. There were two brothers, Johann and Jacob, and they fought like cats and dogs. One of them thought he was smarter than the other one, and they were always competing, and kind of a pain in the neck family. Either one or both of them had some sons, and maybe even a daughter or two, and I think just about all of them were brilliant in mathematics. Daniel was one of the sons. I can't remember which was his father, but he was one of the second generation. And I know the story on him was that one time there was this math competition they came out with. Europe came out with them pretty, maybe not every year, but, pretty frequently. Someone would come up with a really tough problem, say the first person to get it wins this big prize. Okay? Well, the Bernoulli brothers were used to competing with each other on it, and one tended to win more often than the other, and that's why he thought he was so much smarter. So he entered it expecting to win, and sure enough, one of the Bernoullis won. But it wasn't he or his brother, it was his son beat him, okay? He wasn't expecting that, never saw that coming. He didn't even know his son had entered the competition. Well, he was so angry with his son that he beat him in the competition. He kicked him out of the house. So it was really a dysfunctional family going on here. I'm wasting way too much time on it, but math is full of some pretty interesting history. Well, how did L'Hopital get into this? Well, he was a student of one of these Bernoulli brothers. I think probably studied with some of the next generation of Bernoullis, so he had really good peer support and also very good things. But what L'Hopital was really good at is communicating mathematics. So he took it on himself to write a calculus textbook. And what he wrote was probably the finest calculus textbook that had been written to date. Now remember, calculus was just a few generations old now, and the Bernoulli brothers had done a lot of advancing calculus and making it more understandable and stuff, but I don't think they were all that interested in being communicative, okay? They were just interested in being brilliant. But L'Hopital took that and made it so anyone could read it and understand it. That was his skill. And when he wrote his book, he took this rule that he had learned from whichever, I think it was Johann Bernoulli, and put it into his text, giving Johann Bernoulli all the credit that he could. This is from him. I'm not making this up. This is from him. This is a real handy rule to use. But because it showed up in his text, everybody, probably because they didn't really like the Bernoullis that much because they were so arrogant, they started calling it L'Hopital's rule. Oh, and boy, did that ever make Johann Bernoulli mad. I mean, furiously mad. And that's the background here. It's L'Hopital's rule, but it really came from, I believe it was Johann Bernoulli. But we'll get to that in a minute. So, we need to figure out what we're talking about here. What do we mean by indeterminate forms? I think you hit this way back in Cal 1. Let's review it quickly. You know that if you have a number like 17 and you divide by 0, that is just impossible. That is an undefined expression. You cannot divide a number by 0. However, if you had 0 over 0, that's what we call an indeterminate form. It may be undefined, or it may actually have a definition. Another one would be infinity over infinity, which infinity really isn't a number. That just means some number is getting really, 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 really big over some other expression that's getting really, really, really big, but we don't know who wins. Does the numerator win and it goes to infinity, or does the denominator win and it doesn't quite go to infinity? Those are called indeterminate forms because they do not guarantee that the limit exists, nor do they indicate what the limit is. There may not be a limit, and if there is a limit, you don't know what it is, if one does exist. So when you encountered one of those indeterminate forms, you attempted to rewrite the expression using various algebraic techniques. And that's what we're going to do first. Here's a 0 over 0 form. Here's the expression. The limit as x approaches minus 1 of 2x squared minus 2, well, when x is going to minus 1, x squared is going to plus 1. 2 times plus 1 is 2, minus 2 is 0, 0 in the numerator, but you also have a 0 in the denominator. Okay? Well, that's indeterminate. We don't know if the limit exists or not. Just because you have a 0 in the denominator, if that would have been a 17 or a 3 or square root of pi or anything in the numerator divided by 0, does not exist. Period. Done. But because it's 0 over 0, we just don't know. So what do? We pull out our Wacom here and we say, well, we can factor this, can't we? Okay, let's rewrite this as 2 times x squared minus 1 over x plus 1. Well, you can factor that even further and make it 2 times x plus 1 times x minus 1. Oh, you thought you were through with factoring, didn't you? No way. Over x plus 1. Well, look what happens here. You lose that denominator. And this is 2x minus 2. And when you plug a minus 1 in there, that gives you minus 2 equal minus 4. So there's a limit. That limit does exist as x approaches minus 1. Okay? Why? Because you factored it. You use algebraic techniques to simplify your rational expression that gave you an indeterminate form, and you came out with x equal minus 4. Now here's one. Limit as x goes to infinity of 3x squared minus 1. Well, that certainly is going to infinity, because if x is going to infinity, square a huge number and it gets even larger, multiply it by 3 and it gets even larger still, subtract 1 from it and it makes no difference at all. It's still an enormously large number. Do the same thing down here. Square a large number, you get a very much larger number. Multiply that by 2, you get a very much larger number than that. Add 1 to it, that doesn't make much difference, but you still got a very large number. But we don't know. Infinity over infinity doesn't tell us much. But here's what we do. Divide everything on numerator and denominator by 1 over the maximum power of x, 1 over x squared. So this would be 3x squared over x squared minus 1 over x squared over 2x squared over x squared plus 1 over x squared. Okay? Well, this goes to 3. This goes to 0, because 1 over an incredibly large number is going to 0. This is going to 2, and this is going to 0. So you got 3 over 2, 3 halves. That does have a limit. Okay? So there are the techniques that we have. Simplifying your expressions using simple algebraic techniques. One of them factoring, one of them multiplying by least common denominator in the numerator and the denominator, or actually dividing by the least common denominator. Well, dividing by the maximum power. Okay, that's a better way of saying it. Occasionally, you can extend these algebraic techniques to find limits of transcendental functions. Here's one. As x is going to 0, e to the 0, or 0 times 2 is 0. E to the 0 is 1. 1 minus 1 is 0. And this is e to the 0 is 1. Minus 1 is 0. Well, again, you can factor this. This would be e to the x plus 1 times e to the x minus 1. Now, it may not be something you recognize that as factor, but try it. Foil it. E to the x times e to the x is e to the 2x. This would be minus e to the x plus e to the x. That adds a 0, minus 1. Sure enough, that does work. Over e to the x minus 1. Well, these two go out, and that then gives us 1. Because e to the 0 is 1. No, I'm sorry, is equal to 2. Okay. E to the 0 is 1. 1 plus 1 is 2. High level math today. Okay, so even though that produces the indeterminate form, by doing the factoring, you can get it to 2. Okay? Any questions on that? So that's one thing you can do if you have an indeterminate form. See if some algebraic technique will simplify it. If it will, do it. See if you get a form. Not all indeterminate forms, however, can be evaluated by algebraic manipulation. Not every expression is factorable. This is often true when both the algebraic and transcendental functions are involved. Okay, so here we have an expression like we had before, e to the 2x minus 1. You could factor that, but when you do, you're not going to be able to divide anything out. And sure enough, this was 1 minus 1 is 0, and this, as x goes to 0, is 0. Indeterminate form, there's no way to algebraically manipulate that to simplify it. So are you dead in the water? We'll find out. No, you're not. Okay? Now they try another way, and they say, well, let's do e to the 2x over x minus 1 over x. Well, e to the 2x over x is an infinite expression over x, which is an infinite expression. And this is, I'm sorry, this is e to the 2x as x is going to 0. That would be e to the 0, which would be 1 over 0 minus 1 over 0. Hey, that's infinity minus infinity. That doesn't help us any. But that's another indeterminate form. Which of these infinities is winning? Does this one win and the whole thing's going to infinity? Or does this one win and this is reducing that to something simpler, less than infinity? That's a weird way to talk about it, but that's what is happening. Okay? Of course, you could use technology to estimate the limit. For instance, if you did the graph here, then you see, hey, it's not defined there, but sure enough, it looks like x equal 2 is an answer. And we saw that before. We could do, no, we actually didn't do this one. Okay? But this shows us that, no, I'm sorry, x equals 0, y is equal to 2. Okay. So, it appears that as x approaches 0, y does approach 2. That would be your limit. But you'd have to do it graphically, and if you're not careful, you could have things blowing up in here, and that would be problematic. So you have to be careful not to have it blow up. Alright, you could do that on a table and let it go closer and closer to 0. That's getting closer to 2 from the left hand side, closer to 2 from the right hand side. So your assumption is you are going to 2. That's a long way to do it. Okay. Is there an easier way? Yes, this is where L'Hopital's rule comes into play, and here's what it is. To find the limit illustrated in that example, we can use a theorem called L'Hopital's rule. Didn't come from L'Hopital, it came from his professor, Bernoulli, but everybody called it his rule because he wrote it up in his calculus textbook. That theorem states that under certain circumstances, and we'll talk about what those are, certain conditions, the limit of the quotient of f of x over g of x is determined by the limit of the quotient of the derivatives. Interesting. Okay? So, to prove this theorem, you can use a more general result called the extended mean value theorem. Okay? Now, if f and g are both differentiable functions on an open interval a to b and continuous on the closed interval a to b, so they're differentiable on the open interval, continuous on the closed. Now what that means is that the ends, they could be going to infinity. They're continuous there, but they're not differentiable there. Okay. Such that, but the g prime of x cannot be 0 for any x on the interval a to b. F prime could be, but G prime can't. then there exists a point C in the interval a to b, the open interval a to b, such that f prime at C over G prime at C, and if you think of the definition, f prime would be f of b minus f of a over b minus a, and this would be g of b minus g of a over b minus a. B minus a's go out, so you just have the difference of this over the difference of that, okay, between those two limits. Now, L'Hopital's rule then says let f and g be functions that are differentiable in the open interval, same as before, containing C, except possibly at C itself. It may be at C is not differentiable. Assume that g prime of f of x is not equal to 0 for all the x's there. If it were, throw it out. We can't use L'Hopital's rule. Except possibly at C itself, and there g prime could be 0 there. It's okay. Okay. If the limit f of x over g of x as x approaches C produce an indeterminate form, 0 over 0, or actually one of the others, we'll talk about those in a minute, then here's what L'Hopital's rule says. The limit as x approaches C of f of x over g of x, if this thing, that limit gives you an indeterminate form, then take the derivative of the numerator and the denominator and evaluate the limit at the same place of those derivatives, provided the limit here exists. And that's why they say g of x cannot equal 0, because if it did, you'd have to throw this out, except possibly at the point C. It maybe could be equal to 0 there, but if it's anywhere else 0, you have to not use it. Okay? Now, if this limit exists, then the limit of this exists. Or, if this is also an infinite limit, you can then do it again. This result also applies when the limit of f of x over g of x as x approaches C produces any of the indeterminate forms, infinity over infinity, minus infinity over infinity, infinity over minus infinity, or minus infinity over minus infinity. Any one of your infinites over infinites, or 0 over 0. Those are all considered indeterminate forms. A lot of blah, blah, blah. We've got 1 minute. Let's see how far we can get. L'Hopital's rule can also be applied to one-sided limits. For instance, if the limit of f of x over g of x approaches C from the right, and it produces if the limit of f approaches as x approaches C from the right, produce an indeterminate form 0 over 0 at C plus, then you can still do the same thing, provided the limit exists or is infinite, and then you can still go from there. Now, I don't think we're going to have time. We don't have time to do example 1. So that's where we'll be starting next time. So we did get started in 5.6, and we're on page 347, top of the page, and that's where we'll pick up next time. There is a little blurb in your book on page 346 on Guillaume L'Hopital, and he has quite a long name. I won't say it all. I can't pronounce French very well at all. He's credited with writing the first text on differential calculus in which the rule publicly appeared, and it was recently discovered that the rule and its proof were written in a letter from Johann Bernoulli to L'Hopital, and he said, I acknowledge that I owe very much to the bright minds of the Bernoulli brothers, have made free use of their discoveries, said L'Hopital. He gave them credit and everything else, but everybody still called it that. There is a little blurb at the bottom of page 345 on counterexamples to L'Hopital's rule. If you want to look at that, you could do that as well. But we'll start next time on 347. Now, since we didn't do an example in this section, there'll be no homework problems here, but you have plenty of them to do from 5.5. All right, any questions? Any whatsoever? I'm sick and tired of sharing, so I'm going to stop sharing. And unless you have some questions, I'll go on and end the meeting for everybody. Any last thoughts, questions? None? All right, take care. We'll see you on Wednesday, okay? I'll end the meeting for everybody then. Bye-bye.
All right,
Okay, take care.